Right, let's continue this mini course in elastohydrodynamic lubrication. This is the second part, and this time we'll discuss the film thickness equation, or how to compute the thickness of the lubricant film in an EHL contact. So we'll see if we can compute the thickness, and we will discuss then the film thickness equation and the parameters that are included in this equation. We will take a look on a simple example, and we will also say a few words about the maximum pressure that may occur here. And first of all, we might think also about why do we really want to know the film thickness. Well, it's pretty obvious, isn't it? I mean, the thicker the film is, the better it lubricates. And if you have been studying lubrication for a while, you have seen this curve a number of times. It's the Striebeck curve, and it tells you which lubrication regime your machine component is operating in. So if you are operating at low lambda, this lambda is the ratio between the thickness of the film, or the minimum film thickness, and some measure of the surface roughness. In this case, it's the RMS surface roughness height. If this ratio is high, that means it's a thick film in comparison to the height of the roughness. So the higher it is, the better the lubrication, and you are here in the full film. If you have a low number, you're in the boundary lubrication, and you're somewhere in between, you are in the mixed lubrication. In the boundary, the whole load is carried by the asperity contacts, while in the full film lubrication, that's what we aim for, the load is carried by the film itself. Sometimes you use numbers. The lambda below 1 is boundary, lambda over 3 is full film. Good or bad, we will come back to that later. It is at least a number. Really, the reason to find the film thickness is that, as I already said, is that the higher the lambda is, the lower the risk is for different risks of damage. The typical damages that can occur in a non-conformal contact of this type is plastic deformation. You have too high load, or locally only at the asperities, you have too sharp asperities. All these contacts and varying pressures may cause contact fatigue. It can be down in the surface and below the surface, at the surface or down in the surface. It can cause damages called pitting or micro pitting. If you have a very thin film, the surfaces may come in contact, especially when they slide, and then you can reach very high temperatures, and you may have a DC wear, or what we call scuffing. And of course also, if these tiny films are only less than a micrometer, they are very sensitive to particles. So if a particle is entrained, then you have a problem normally. Well, now we know that the high lambda is good, but can we then predict the risk of damage, and can we predict the lambda? Well, we can do that if we can predict the minimum film thickness and also the maximum contact pressure. I will not discuss the maximum contact pressure very much, because if you take a look on the contact mechanics and the Hertz analysis, then you can compute the maximum contact pressure pretty well, and that maximum contact pressure is also a good measure of the maximum contact pressure in an EHL contact. So we will focus on the lubricant film thickness. And to answer the question, then, can we predict this? Yes, we can do that, because there are some simple engineering equations to be used to compute the film thickness. And as I said, the Hertz contact equation too, and we can also correct these for thermal effects and roughness effects, which I will do in later parts of this mini course. First of all, we will start with the line contact problem. In the line contact problem, you have a cylinder and you put that in contact with another cylinder under a certain contact force. We use W here. And these surfaces are moving, so the surface velocities, that's also important parameters here. The shape of the cylinders or the size of the cylinders are important, because the smaller the radius is, the more concentrated contact, the higher the contact pressure is. And of course also the elastic properties of the rollers are important. It's both the Young's modulus and the Poisson number for both cylinders. And finally the properties of the fluid or the lubricant here. So in this case the important parameters is the lubricant viscosity, the dynamic viscosity. We normally use eta, and also the pressure viscosity, the alpha I showed you before. So this is the full list of parameters. As I said, it's the load, it's the speeds of the two surfaces. If they are the same, it's a rolling contact. If they are different, it's a partly sliding contact. The radii and the lubricant parameters, again, the viscosity at atmospheric pressure, the pressure viscosity relationship or the alpha parameter, but also the viscosity temperature, beta, coming back to that later, and the thermal conductivity, coming back to that too later. Again, elastic modulus, Poisson number, but also the hardness. If you compute the maximum pressure, you really need to compare that to the hardness of the surfaces. If the maximum pressure is higher than the hardness, you have a problem, because then you may expect that you have plastic deformation of the whole contact, and that's not good at all, because then you create an indent in the surface. And of course, in order to determine the film parameter, you really need to know the surface roughness. So over the years, people have tried to simulate the EHL contact. We have also done the measurements, as you saw in the optical interferometry. The optical interferometry has helped us very much to understand how the film is formed and how it looks like. But you also need simulations to be able to compute the thickness for various combinations of these parameters. And when you do that, you actually solve Reynolds equation. You remember that from lubrication theory. You must have some equation describing the film profile, which is this one. This is the cylindrical shape plus the deformation. You need some equation to compute the deformation, you need a viscosity relationship, you need a density relationship, and you need a force balance. That's the pressure, the generated pressure in the film must carry the load. And you can see here that in order to compute, in order to solve this partial differential equation, you need to know the film thickness, but in order to know the film thickness, you need to know the deformation, and in order to know the deformation, you need to know the pressure. In Reynolds equation, you also need to know viscosity and density, and they are also both equations or relationships including pressure. That means that this is a very nonlinear equation, so you have to solve this iteratively, and it's over the years it has been shown that it's pretty tricky to solve this equation, but people have managed already in the 60s and 70s. People solved this equation numerically, and they came up with a really nice kind of summary of the result. So they made a large number of numerical solutions of this EHL problem, and they came up with an approximate equation showing how the different parameters influence the film thickness in the EHL contacts. So in this case, the line contact, it is shown that only 6 parameters are involved. It's the average surface velocity. We all normally call that also the entrainment speed. So it's just the average of the two speeds. It's the load per unit width. Remember, this is a line contact, so you must express it in Newton per meter. It's the viscosity at the atmospheric pressure. It's the pressure viscosity coefficient, the alpha, the effective elastic modulus, which is a kind of combination of the two surfaces properties, and the effective radius, which is also a combination of the two radii. And then you come up with a nice equation of this type. So you can see here, clearly see the influence on the minimum film thickness of the different parameters. So you can see the radius is pretty important. The speed is even more important because this number is high, the exponent is higher. The viscosity is important. The Young's modulus is not, or the effective Young's modulus is not that important at all, because this number is pretty small, so it really doesn't matter which metal you are using here. But remember, this equation is only valid for non-conformal hard EHL, so you mustn't try to use this for an elastomer, but it's pretty okay for metals, or like steel, I would say. The pressure viscosity coefficient is important, and load is maybe not that important. It's this number is pretty small, so it doesn't really matter much. If the load is doubled, then the film thickness is not influenced very much, because what is happening instead is that when the load is doubled, the contact region is growing, so a bigger part of the ball is, or the cylinder is carrying the load. And since the lubricant is in a glassy state at the center, it deforms around this glassy lubricant, and it can't really squeeze it out. So it's of that reason the load has a pretty small influence. It should be a negative sign here, of course, since higher load means smaller film thickness. You can do the same for an elliptical contact, which is a more general case. Then you can, elliptical contact means more or less any shape from a line contact to a circular contact. But this is which an elliptical contact is what you typically find in a ball bearing, for example, or maybe in a gear too. And you can see the same type of equation here, a little bit different exponents here. Here in this case the Young's modulus is more important, the load is even less important, and here you have a term taking the ellipticity into account, and the ellipticity is defined as the ratio between the combined radius in the y direction and in the x direction, and you can compute it in this way approximately. So by using these two equations, you can compute the film thickness in an EHL contact pretty well. So an example here, a ball on a lubricated surface. Assume that the load is 1000 newtons, the radius is 35 millimeters, you have a viscosity of 45 millipascal seconds and an alpha, which is a typical value here, 10 to the power minus 8, and the speed is it's a rolling contact, and it rolls at a speed of 0.1 meters per second. If you solve this equation, which is pretty easy, you will find that the minimum film thickness is something like 41 nanometers. The contact spot is by using Hertz analysis, I would say, you can see that the contact spot is 1.2 millimeters and the maximum pressure is around 1.3 gigapascals. You may check in Tribology ABC when using Van Beek's calculators, see if he gets the same. A funny thing with EHL is that it's actually the inlet that controls the thickness of the film. So the lubricant captured here or entrapped here in the inlet is drawn into the inlet, brought into the contact here, and what is happening here doesn't really matter much for the film thickness, because what is taken in here must also pass through the contact. So the film thickness is controlled by what is happening here. But then you must remember also when especially in a sliding contact, that the lubricant is pretty much shared at the inlet, and this sharing may heat up the lubricant before it enters the contact. So you really need to take the viscosity in the inlet, use the viscosity in the very inlet in your film thickness equation, because the viscosity may be strongly reduced due to this sharing. Remember also that the compression of the lubricant will increase the pressure, the temperature, because it's a very rapid compression. On the other hand, you have the opposite decompression in the other end of the contact, so it's a kind of reversible process. Again, sliding motion will create more heat than the rolling. And then you also need a relationship between viscosity and temperature, and this is a typical relationship, and this is a simple equation. It isn't very accurate, but it's okay in a certain temperature range. And now we have a new parameter here, beta, which defines how the viscosity varies with temperature. For example, here you have a few examples. Again, an ester has a low number here. That means that the slope is lower for this curve for the ester. That means it has a higher viscosity index than, for example, this one, the naphthenic mineral oil, which has a pretty poor viscosity index. But from this beta is an important parameter. The thermal conductivity is also important, because an oil is a pretty poor, has a poor thermal conductivity, so the heat is not conducted away very easily from this thin film. Typical numbers you can find here: naphthenic mineral oil, again the worst numbers, while an ester has the best numbers, highest. Even if it's a poor number here, a low thermal conductivity, it is much better than the mineral oils. So, and then you can correct the film thickness by using a correction formula. There are a number to choose among, but I have been choosing this one. I've been using this one over the years, and so you actually compute the thermal minimum film thickness as you first compute the isothermal, and you multiply it by the factor CT. And this CT is computed from this expression, which involves the maximum Hertz pressure, it involves the effective Young's modulus, it involves the slide to roll ratio A, and something called the Brinkmann number, which is a non-dimensional number, including the beta, the viscosity at the atmospheric pressure, the speeds, this is the entrainment speed, so the average speed, and the thermal conductivity. So now you see why the beta and the lambda is used, is important. So that ends part 2. Now you know how to compute the film thickness, and you also know the important EHL parameters are. Next time we will discuss rheology and friction. Thank you very much.